Check. Oh, that is on. Hello. I have a really commanding voice anyway sometimes, so going handheld today. We have some special guests, but here I'm talking to you about going from prototypes to production using nerves to be able to create some connected hardware. But first, I want to take a moment to be able to sort of reflect about how in every talk that I ever put together, it seems like you get to the venue and then you end up watching other people talk, and it's just so inspirational that you just, at the end of every one, you're like, oh, that's really cool. I should rewrite part of my slides because I'm crazy. Well, I went and I didn't really necessarily go that far this time, but I do want to touch on something, and that is some inspiration that I took from our opening keynote yesterday. As she was talking through the realities of what it's like to build communities in software, I started to feel like similarities in the landscape of hardware. So at first I want to talk about what is the landscape? What is the feeling like when it comes to hardware? And from the top level perspective, when she spoke about the feeling of building these communities and what it's like to be able to be interacting with other software engineers and sharing knowledge, it seems sometimes like when it comes to embedded hardware, that's not necessarily always the case. And a lot of times what you'll get is these like siloed workforces of people building hardware that behind closed doors that they have something very special that they're making, and theirs is going to beat yours to market. And in early software, things were a lot like this as well. And then open source sort of just came along and accelerated everything. And so I sort of had this mentality of like, you know, what was stuff like, and where are we going next? And I envisioned this sort of infinite pattern that we fall ourselves into, where back in the day, and I'll make that an open timeline, we worked on things like hardware products. We built things that made our lives feel better, physical objects. We made like CD players and stuff like that. And there was software that ran on those hardware products, but the intent was to be able to get the hardware out. And then throughout the time, we ended up bringing on a lot of application software developers around maybe like mid-90s or so. People started getting into the actual just the software aspects of programming, where you're making systems that are just able to orchestrate and bring together workflows. And then along came web development and just blew everything away. Once the web opened up, it seems like we started to embrace the paradigms of open source software and sharing knowledge between other groups. And in that transition, it sort of felt like the hardware design companies, the hardware that we were building, it has some, I should say, comparatively to just what a software developer gets to feel like, it has a few sort of disadvantages in that, yes, it does take a little longer to be able to iterate these kind of things, because when it's in the field, it's really difficult for you to just apply a software update to be able to fix some hardware problem that you may have encountered. So you got to get it right, you have to spend time, and that usually delays things to market, and thus that ends up spreading out those timelines further and making that property more valuable, that intellectual property. So where are we at today? Well, we're advancing through the forms of web development into an area where it's no longer connectivity with desktops and laptops and tablets. And these are the things that we're used to, but our lives are now being brought in tune with sensors and data and everything, the Internet of Things. I said it. That's it. I'll let that one go for maybe I'll just do it once. But now everything's going to have an IP address, and we need networks, and we need things to be able to, well, we have the capabilities of doing this, is what we've answered. Whether or not we should, that's yet to be determined. But we have the capabilities of doing this. And the people that are on the edge of being able to just reach down and grab that sensor data, it's oftentimes now presented with a lot of web developers. Because now with advancements in web technologies like adding into the Phoenix framework, having the ability of having channels, we have this fast-moving, fast-paced group of developers giving them the capability of saying, hey, hardware guys, I need this. And if we could just extend their arm a little further so that they could actually build it themselves as well, then they can create new, innovative products with having little knowledge or little experience about being able to get started with hardware. One example of which is somebody thought that smart water, I guess, wasn't smart enough, and that instead it needs to have its own smart water bottle. We too can make creative products like this. No longer are you bound by the chains of thirst to tell you that you should drink water. Mind you, it got almost over $500,000 in backers. So these things are real, and people are spending their money on them. But the hard part about it is that hardware is hard. I mean, if it wasn't hard, we'd all be doing it very easily. And there's a lot of stuff that's bringing to the market the ability for us to do this. I mean, it's so hard. Hard is in the name. So over the years, things have been able to start to get a little bit easier. There's been advancements in technology that gives people the ability of getting started faster. Arduino is one. It's a low-level microcontrollers that you can then have very easy, familiar to use IDEs. It's more welcoming to software developers. It's got a community of libraries and people behind it that share a lot of knowledge. And so for new people coming in, there's really easy and convenient places to be able to go to get started. And then further along came Raspberry Pi Foundation, where they provided single board computers that run Linux. They're more powerful. They have higher connectivity to the world. They have higher languages that you can run on them. And aside from all that, we have this movement now towards open source hardware and open source software that runs on it, thus giving us this now freedom to no longer have to depend on using C, C++, or the sort of shelled, jailed knowledge that the groups of hardware developers contain. So what's actually bringing these things forward? You know, what are we talking about in this case? Well, for two audiences specifically, and the birth of this happened pretty much in the maker market. Maker Faire, Make Magazine, Raspberry Pi Foundation, they're putting together programs and literature to be able to make it more accessible for people to build this stuff. Now, I had an experiment on this my own as a maker, so it's sort of where I started tinkering with things. I originally started using Arduinos, and everything was great until the moment where I decided, I want to put this thing on the internet and be able to communicate with it from somewhere else, like my cell phone. And that got to a point where it was really difficult with just lower level languages and lower level processors. Having the experience of being able to use higher level languages, I expected more. And so here's a snapshot of one of my first projects. We built an embedded system into, this is using some Nerves devices. So we have a wireless embedded Nerves device in a motorcycle jacket that synchronizes with the computer that's on the motorcycle so that the blinkers, the stop indicator, and also the ECU would be able to be communicated with from a cell phone. So the way that's actually worked in the long term was really cool. You just, it connected over Bluetooth. So as you walk up to it, your phone connects to it in your pocket. It realizes you're wearing the jacket, so it just starts the bike for you. And then when you get off of it and walk away, it just shuts off. Safety first, it reads to make sure the parking is that it's not in gear when you get off of it and everything. So. From there, I ended up building some other devices, hacked together some temperature controllers and brewing systems for being able to do fermentation control for brewing beer, because that's really important when you're hacking on hardware and things don't go your way. Nothing beats that than a nice, tall, cold beverage. But Nerves and these devices, they're not just for makers. They're also being able to be used for professionals, for production. This is a beautiful shot from the mezzanine at a distillery in Pennsylvania that uses Nerves to be able to automate the still. We read temperature sensors from the probes in the top of the stacks and then use that to be able to actuate water valves so that we can control the amount that it steps down on the still. which allows us to be able to very fine-tune grain the exact sort of percentage by volume of alcohol that actually gets output from it. But not just them, there's a wide variety of people that are using NERVs in production, including National Association of Realtors. I know Chris is here, and he's going to be chatting about that. We have Rose Point Navigation. They use it on boats, Social Still, Latote, and FarmBot. And so for those of you who don't know me, or may, I work for Latote. And in production, we use NERVs to be able to automate a lot of our warehousing equipment. There's a certain level of service that's not really available in the market for what we need to be able to do. So we want to build custom devices and control the workflow from end to end, giving us the ability of connecting our embedded devices running Elixir all the way up to our SaaS application running Elixir using this kind of connectivity. And so before we go into talk about what exactly NERVs is and to break that down, I wanted to just hit on this point of what it's like to be able to create these devices. And since this talk is from production to prototype, I thought nobody better to be able to do this than FarmBot. And so FarmBot is a device that runs NERVs. And here we have Connor Rigby from FarmBot. I'd just like to give him a chance to be able to give you thoughts on his experience using it to build the fun-looking, awesome robot that's in front of you right now. Connor?
Do I need to sit there?
Yes, you will. Okay. This is the fun moment.
I'll put it wherever.
It's like giving a demo, swapping a mic pad.
Yeah, easy.
All right, here you go. There you go, Connor.
I'm going to try to stick this right in my pocket. Can you guys hear me okay? I'm not good at speaking in front of people. Can I make this go to my oh yeah, we'll do it that way. So we'll give a brief history real quick. I don't know how well you can see that. It was taken quite a long time ago. That's what it used to look like. It was just a mess over bins and stuff. And we didn't even have the Raspberry Pi. We used a Raspberry Pi to control it now. We didn't even have it. We were just hardwired in there with an old laptop. So we called that the Dark Ages. It was written in Ruby. It apparently used NetDB, which I did not know. I was not part of the company at this point in time. Oh, we did. We put it on the Raspberry Pi, and it was terrible. When I first started, this was the installation instructions. We gave this to people in production. We told them, install Raspbane, apt-get upgrade, git clone, blah, blah, blah. Let's see, I think I got a list of it here. Oh, so that was before. This is what it looks like now. And just this huge thing. It took like 2 hours just to set up the device. It was terrible. Back then, when you wanted to update it, you just use Git. It's magic. Easy. So now it's super easy. We've got an image on GitHub. We just host it there. You download it. You burn it just the same as you would as Raspbane. And then it all just works. There's an SSID that comes up called FarmBot. You click on it, and it captive portals you. Updating super easy now. You just click the update button. Done. The rest of that's his. Can you make this go to Chrome? I don't know. Or sure. It'll be easier. You want to drive it? Yeah, sure. Improv. It's easy. Okay, so I'm going to give a quick demo, and we're going to hope it works. I think I spelled that right, and we'll lift the robot up at the table. Yeah, if it here,
sure. Yeah, I got it.
Yeah. You just sure. It's not that heavy. No, it does not work. So hopefully you guys can see that, and hopefully our JavaScript loads.
Oh, that's the internet here.
Yeah.
Live demos are fun.
I've got it.
Does anybody know magic tricks?
Make React work faster. There's probably Webpack going on in the background.
Switching networks. The network never works.
It never works. Huh? I've got it tethered on. I've got my phone running for Tether too. There's one.
Yeah, I'm attempting to tether now. Even that is slow. Oh, there we go.
There we go. So,
Okay. Try again. And LTE.
hey, magic. That's the hard part.
Yeah, I'll save your password.
Yeah, go for it. It's my demo one, so it don't matter. You can control it while it's at my house. So this is extremely difficult to do. Oh, there we go. Yeah, I think that you want to hold the table there a little bit. So we've got a pretty basic interface that sounds like is binding real easily. I haven't transported this thing since it was brought to me, so I don't know how well it actually works after being ripped apart and in my car for 3 days. We call this part here NASA control panel because there are just too many options to configure. There we go. So hopefully that makes it work a little bit smoother. Oh, there we go, much better. So it's just a big CNC machine, basically a 3D printer with a magnet on the end of it right here. And unfortunately, I don't have any actual plants here. They didn't want to come with me. But we have this whole sequence builder here that lets you control how it moves around in its plane and, you know, move its plants around. And I don't know if it'll actually run it. We'll try it. I don't know what that is.
That's a dictionary.
I don't speak OS X. Hey, that did work, kind of. So it kind of works. That's about all I have to say for it right now. This is not our full-scale one. Obviously, it comes in a much bigger package. I call this my FarmBot dev kit. And it started out with Ruby. I rewrote it in probably about a month in all Elixir using nerves.
Cool.
And yeah. What's it do? It grows plants. Sorry, I missed that part, I guess.
It does the farming for you, so you don't have to.
Yeah.
All right, I'm scared of this thing. We got to set it back down
Yeah,
on the stage. I'm just scared of it falling off. Nothing beats. Yes.
Yeah.
I feel. I'm feeling pain for the robot. All right. And putting mics on and taking mics off. Beautiful. All right. So that was FarmBot. So now I want to just talk about what it's like to be able to actually build devices using Nerves, and what is Nerves itself. Well, Nerves is built on using Erlang, but we gravitated towards Elixir. And with Erlang and Elixir, we found that using these constructs to be able to create robots, to create hardware and machines, felt very natural, and for several reasons. First off, well, we all know the fault tolerance story. You've got the ability of supervising a network of different connected hardware, or you've got different sensors. And having fault tolerance gives you the ability of monitoring processes that you'd have that are parsing protocols, or maybe you'd have some ports that are open that are reaching out and communicating with sensors or other devices on your network. In addition, the pattern matching story is very beautiful when it comes to being able to communicate with these devices and sensors. The data streams that are coming in, this makes it really easy to be able to just enumerate over them and break them apart and be able to understand them a lot better. And also connectivity. As I said, when it comes to lower level pieces of hardware and microcontrollers, it's really difficult to be able to get out to the internet with them, to be able to reach outside and get them connected online. Being able to use Raspberry Pis and other systems like that give you the ability of getting on the network and being able to get out there. So what exactly is NERVs? Well, in our approach, what we have is we basically take Linux and Linux kernel with some userland space stuff, and we marry that with your application that lives inside of the Erlang VM. So we take Erlang VM and we take Linux, and we basically take Linux's initialization systems that would normally boot like systemd, udev. We replace them completely by getting it right to the Erlang VM, which means that all of the initialization of all the subsystems happens from as fast as possible inside of your application. And so this lower level piece here, we call this NERVs platform. And so this is essentially what kind of Linux kernel, what kind of system you're going to be running on top of. And the flexibility that you get here with Linux is that you get all of these drivers and all of the low-level details of the work that's been done over the years to be able to support all of, connected Wi-Fi chip this and blah, 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 all this kind of different stuff you'd want to plug into it. And in a way that we support a lot of popular platforms using that. So with NERVs, you can get started on a lot of these different devices out of the box, all of the different Raspberry Pis, Raspberry Pi Zero, including the Zero W. I believe there's some ongoing work with that, but I think it's actually pretty much getting there with support. We did a seminar with the Linkit Smart Duo. It's a pretty cool little MIPS processor. It's got a microcontroller on the back of it that's actually connected directly to one of its serial ports. It's pretty neat. It's kind of like having an Arduino and a Linux PC, like all in the same thing. And then we also support other stuff like BeagleBone Black, BeagleBone Green, the Lego EV3. It's pretty fun for doing stuff with robots, and the Intel Galileo. And the nice thing here is that these aren't the only platforms or the only boards that you can use with NERVs. They're just the ones that we officially did the work for and support out of the box. Since NERVs is built on technology called Buildroot under the hood, essentially it's fairly easy with a minimalish amount of work to be able to take any Buildroot compatible board and fairly easily get it up and running into a NERVs platform image that you can then use later. So how do you communicate with some of the outside world? Well, with NERVs, your application has the ability of being able to also include any C and C++ that you might want to bring in. So if you've already had some code that you had written that needs to be able to interrupt in C or C++, our toolchains that we supply as part of the package will automatically bring that stuff and cross-compile it to be able to run on that target. In addition, we have a series of frameworks to be able to get you up and running and started. As I mentioned, once you're inside of the VM, since we replaced a lot of the traditional initialization systems, it's up to you to be able to bring up some of these subsystems. And so we provide LEDs, firmware update mechanisms, ncurses libraries, Wi-Fi, Ethernet, GPIO, a great deal of helpful things to be able to use inside of the Erlang VM. And then for distributing your systems or for actually burning it onto the cards, we're built on something called, we use something called FWUp. And one of the NERVs core team members, Frank Hunleth, wrote this utility. It doesn't actually have to be used only with NERVs. If you're doing other embedded hardware development and you wanted a firmware update mechanism that can just flash over stuff and do firmware updates, this actually will do it with nice configuration value as well. And so what essentially our firmware looks like that gets burned onto the device, we have the boot partition. This is where your bootloader is going to go. And then we have two firmware partitions that we lay out. We only make one of them active at a time. And then we also give you extra data partitions. Everything on this side actually is read-only. And that's nice because if you yank the power out of it, which is expected in these situations, it's not going to corrupt things. And you have read-write partitions where you can actually store some data and persist it. Those may become corrupted, so there's often strategies you'll find where you'll boot into the read-only because you know it's going to work, and then you'll just triage in case something happened to your read-write partitions, and maybe you just flash them back from a seed so that you don't actually brick the device. You'll just be able to recover. So there's some different design techniques that we use in this case. There's for soft real-time, you can just basically go and use the Erlang VM to communicate with some packages that you have, one of which in this case is Elixir Erlang, and that contains support for being able to use GPIO, communicate with SPI devices, as well as I2C. And that might be like a temperature sensor, and you can just ask for that information periodically. If you have more hard real-time deadlines, you can use nerves in a way that allows your Linux machine that's still running soft real-time to just sort of supervise and monitor connected devices and hardware that you might take a microcontroller that's running your hardened deadlines to communicate with a sensor and then periodically pull it or get some interrupts on when there's information available. That way you'll just offload the hard real-time processing and you'll just sort of do what Elixir and Erlang do best, which is send messages and make sure it's alive. To get started with nerves, it's really easy. You just type in the world's longest URL. We're making that a little shorter, but we got to get our SSL certificates up. You can actually find this on our Getting Started pages, which is the next slide. Anyways, you have to install an archive using Mix. And basically with nerves, we'll compile anything as long as it compiles under Mix, because that's the environment that we bootstrap around. And then you can use our new project generator to be able to just get up and running with mix nerves.new. As I said, we have a great series of docs that are on hex docs. You can check out the Getting Started guides here. It'll give you all the other information. There's a few utilities like FWUp that you'd need to install on your system. And if you want to be able to just get down and dirty with it, you can actually just check out our Nerves example repository, which we keep up to date with the latest versions of Nerves, where you can do stuff like blink LEDs and play around with GPIO. And there's also a bunch of different examples for getting connected to networks and doing some more advanced topics as well. So I had the pleasure of having Connor make a fool of himself and do a demo, so now it's my turn. And these things do always go perfect. So I'm pretty sure that everybody can hear me in this case. I'm just going to set this mic down for now and escape out of this. And I'm going to try to get us to a reasonable, oh, that's pretty reasonable. That's not as reasonable. We'll get a realistic-ish resolution. It's more reasonable. It's a little bigger. All right, so I just have a folder here set up. And the first thing, like I said, I'm going to do, I already have the archive installed, so I can say mix archive, and it'll list, I've got Nerves Bootstrap already installed. So that means I can say mix nerves.new, and I'll say playground. And this is going to use our new project generator. It's going to ask us some questions like, do we want to fetch and install dependencies? Oh, that always works at the conferences. Why not? Yay! I'm on my phone still. It's a farce. I'm not magical, really. So the nice thing is we give you a little bit of information when you're all done. We let you know, oh, you should CD into your project, and you should get started like that.
Can you move the terminal over a little bit?
Oh, sure. Cuts you off. There we go. Okay. It's got that buffer line. It's an overscan. All right. So we're just going to go into our playground application. And out of the box, we're set in a mode that's compiling for our host. And that's because sometimes we need to be able to build some utilities that give us ability to communicate with our target. But I'm just going to pass this over. We're going to go here and we're going to say, oh, we're going to set our target. So today we're going to play around with Raspberry Pi 3. So we're just going to say export mix under target equals rpi3. And I'll say mix steps.get, because this always works as well. And what that does is it's just going out and getting dependencies from hex. That includes all of the stuff needed to build, as well as, like this, as I said, the system and the tool chain. That takes care of it for you. And we're just going to go crazy, and we're going to say mix firmware. And that's going to put together, it compiles your application, it produces an OTP release, it marries it with the Erlang system and all the cross-compiled code that goes with it, and then we're done. We're back to a prompt. So I'm just going to pull the SD card out of the back of this guy, get my trusty little SD card adapter, slide it into my laptop, and let's burn it. Automatically discovers the SD card that's in there. We'll say, yep, that's the one I wanted. Type my super secret password into the window. All right, now I got an SD card. Pop it into the back of my Raspberry Pi, and let's plug it in and see it lit up. With this power cable, I also have console access to be able to watch Linux boot. And here's one thing we can see. We've booted into Erlang init in 2.87 seconds. So there we are. Now, here's the trick. For newbies and new beginners, we boot Raspberry Pis directly off of the HDMI port because people hook them up that way. They have a TV and everything. So there's a little bit of work that needs to be done to be able to switch this over to use a more advanced connection method like this. We're probably going to work on switching this to use this mechanism in the future. But for now, we're just going to reconfigure the system. And so what I'm showing here is we're going to just create a new file in our config for the application. And we're going to say, we're going to add root file system, and everything under this directory is going to be applied as an overlay. So we'll put a file in ets, and we'll say erl init.config. And we're going to paste this new file here, and magic behind the hood. We're switching the UART port, which is what this is telling us, that the Erlang shell is not actually putting us in the right place. So one other thing that we need to do is we need to change our configuration to be able to make it apply that overlay. So we'll tell the config for NERVs firmware to set the root file system additions to config root fs. All right, that's where we put it, and we'll save that, and let's go back to our terminal, and let's just mix firmware again. As Pierre says in his talk, it's so much easier with SD cards to swap this stuff around. Because you can save them, put them on the side, flip back and forth. So we're just going to burn. Do 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 do. All right. Now, boot it back up. And here we go. IEX. So we can see here, we can say ls. Hey, how about we do this? Whoop. And that window's off the edge. There we go. All right. So we can say ls. We could say on the root file system, clearly a Linux box in this case. So that's us booting to this. There's one cool feature that I want to show you as well, and that's an addition that we just made to the .5 release of Nerves. It actually has an experimental host shell emulator that we provide. In this case, we're advocating that you want to live most of your life in the VM, and you never want to be able to go outside of that, right? Well, that's not always the case. Sometimes you want to poke around at the system and make sure things are working well. So from within job control, we can start a new job, and we'll say elixir.nerves runtime shell. And we'll connect to that, and now we can just ls cd to /, say ls bin, oops, there we go. Say sbin, we see we have IP link, and just call stuff and get output. And then when we're done, we can use job control to list our jobs. Let's say switch back to the first one in our IEX session. So we never have to really leave the beam at this point. We can poke around in the system. There's some limitations with it yet. That's why I use the word experimental. But we're hoping to be able to fine-tune that a little bit more on a roadmap to 1.0. So real quick, I do have some other stuff that I could play with, but how's my time? What am I? Is it? Oh, great. OK. So I haven't quite made a fool of myself yet, so I'm going to try. I'm trying really hard. All right, so let's blink some lights. Everybody likes blinking lights, right? That is true. I mean, seeing a robot move, that's way cooler, but we're going to blink some lights. So first thing I'm going to do is I'm just going to add in a little module here. This is way overkill, all right? So in our application, we're just going to say blink server. And to save time, boom, I am so fast at programming. And this is just a gen server, like I said, that's complete overkill for blinking lights. But you know, there's nothing like supervising your lights blinking. Anything can happen to them, right? And you know what? I'm just gonna go for broke here. While I'm still on the Wi-Fi, on the good Wi-Fi, let's add in some networking support here, and see if we can truly break stuff. All right. So the way that you lay out a NERVS project, like I said, there's a host section and then there's a target section. In our case here, we can add dependencies just for our host on our laptop that we want to be able to use to build utilities to speak with the target. What I'm doing is I'm editing this to be able to include the Wi-Fi support for the target, and that we don't need that on our host. And in addition, because I'm on good Wi-Fi still, I'm going to steal a line from down here. And this one we're going to use for both. And I'll explain that in a minute. So let's grab some dependencies. Git over phone. Come on. I know you can do it. This is what backups are for. Boom. While that's building, we do have a mechanism for being able to do some fun stuff. Like I said, since you have access to Linux, you can actually load kernel modules. So in our case here, we're just going to configure the application. This is the mix file. We're just going to tell it that there's some kernel modules we're interested in having it start. When my clipboard is happy with me. Oh, yeah, when you copy the new end of the line. There we go. And we need a little bit of config as well. Thank you all for bearing with me. Nobody look at these super secret passwords. This is where things get really hairy because the network hasn't been friendly with us today. But we're going to try it anyways. We're going to switch over to it now. Ta-da! All right. Let's boot it up. And let's have it make some noise while it searches for Wi-Fi networks. And it crashed. I did. There it is. Playground.blink server is not available. Okay. I don't see anything wrong. It's clearly there. And yeah. Well, we're running out of time. I tried to go full force on it. It blinks lights. If it can make that robot move, it can blink lights. We'll leave it at that. All right.